Hello, everyone. We are going to be still talking about Chapter 3 in our textbook. But what we're going to be doing now is we're going to be looking at conformational analysis, but we're extending this to cyclic structures, and we're going to look at the structure of cyclic alkanes, such as cyclohexane and cyclopentane, a little bit more closely. So let's get started. Okay. When I look at cycloalkanes, I have to remember a couple of things about regular acyclic alkanes. Remember, in any alkane, my carbons are sp3 hybridized, and that ideal bond angle is going to be 109.5 degrees. If cycloalkanes were flat, each carbon in the ring would experience angle strain. So if I look at the flat representative, cyclopropane would have bond angles of like 60 degrees because that's what that equilateral triangle would look like. Cyclobutane would have a bond angle of about 90 degrees. If you look at cyclopentane and cyclohexane, I'd have 108 and 120 degrees based on these angles in these geometric figures. And the other thing is, if you built a model and you placed all the atoms in the same plane where the ring was flat, all of the carbon-carbon bonds would be eclipsing rotamers, and this would give us a lot of torsional strain. So they're not flat. So what do they look like? Well, we know some information about the stability of cycloalkanes by looking at combustion data for various cycloalkanes. This shows us that a 6-membered ring is the most stable ring size. If I look at the heats of combustion, I get the smallest release of energy when I have the 6-membered ring. 5-membered ring is also pretty good. So when you think about this, this is the lowest amount of energy. That means that's going to be the most stable ring size. So again, in this section, my models are going to be critical. Build a model of cyclopropane. You really have to bend those bonds and push them together in order to get cyclopropane. In fact, some models won't even let you push them in so far. You can just tell physically that there's a lot of resistance to putting those carbons in that configuration. Remember, these are all sp3 hybridized carbons, so they should have a bond angle of 109.5. But in a cyclopropane, my bond angle is roughly 60 degrees because my ring size is so small. And what I notice is that's a huge deviation from the ideal tetrahedral angle. Now, make the model of cyclopropane, and you're going to see something like this. And what you're going to notice is that I do have these eclipsing sort of interactions as I go across and around the ring here. So we know that that's unstable anyways. When I look at cyclobutane, that's about 27 kilojoules per mole less stable than if my ring has 6 members, the cyclohexane. So I have bond angles about 88 degrees instead of 109.5. That gives me a lot of angle strain. I have some torsional strain because my adjacent carbon-hydrogen bonds are not either fully eclipsed or fully staggered. I actually get some sort of a puckered conformation, which has less strain than a flat. So if you build this, you're going to see that I actually have some sort of puckering here. And that allows a little bit of the strain inherent in that very small cyclobutyl ring and to be relieved a little bit. When I look at cyclopentane, only 5 kilojoule per mole less stable. I have very little angle strain. My bond angles are pretty much close to ideal. There is a slight torsional strain, and what I will notice is that this sort of, if you look at it here, this is kind of called an envelope conformation. Kind of looks like an envelope. And again, make a model of it and you can see this. You can play with these models and sort of, you're not going to rotate, but you are going to move bonds up and down and all around when you look at these different models. When I look at cyclohexane and I see this in 3D, I can see very strongly two obvious forms. I can have a chair form, which is the most stable conformation of cyclohexane. Again, that could change depending on what else is around it. And I can have a boat form. The chair form has got everything in a staggered array. All of these bonds are going to be staggered in the chair. The boat form, all of these bonds are going to be eclipsed. And it's important enough where I am going to actually use my model on the screen. This is cyclohexane. And if I look at cyclohexane, this is my chair. And this would be my boat. You see how that sort of makes a boat? Now this has got a lot of interaction here. And I can tell that there's a lot of eclipsing interactions in this. But if I just pop this down, now I have the chair. And if you make it, you're going to notice that this is the most stable conformation. So this right here is the chair. Here's the head of my chair. My body goes down. Here's my my butt area, and then my legs. So it kind of looks like a lounge chair, right? Head, back, body, footrest. So it kind of looks like a lounge chair. And again, you really want to make these models in order to really be able to understand this. So the boat conformation, you saw it, or if you make a model, you will see it. I have this huge, this is carbon 1, 2, 3, 4, 5, 6. I have a 1,4 flagpole interaction. These two hydrogens get right up in each other's business when they're in the boat conformation. That is not going to be very stable. There are a lot of steric hindrance here. I can also draw a twist boat. This actually has a lower energy than the pure boat, but it's not stable as the chair. This is what it looks like when we consider cyclohexane, you should know the boat, you should know the chair, and we're really going to spend some time analyzing chair conformations, depending on if we have one substituent or two or more. So those are where I really want you to focus your attention. Now, just like with those acyclic alkanes, I can draw energy diagrams, and I can go ahead and work from one chair conformation, go through a half chair, to a twist boat, to the boat, to another twist boat, to a half chair, and then I come down and I'm in sort of the second chair conformation, which if I have a substituent, this is going to be different from that first one. And we'll go through that before. But notice, my lowest energy is the chair. So that's my lowest energy conformation. My highest energy is going to be the half chair. And then I have these twist boats, which are also they're energy minima. So they're not the highest energy conformation, but they're much less stable than a chair. And then my boat is an energy maximum, but it's much more stable than my half chair. If you build the chair, kind of go from one chair to the other by trying to adopt these different conformations, and then you can kind of see those interactions as you go from one side to the other. But this is sort of this relative energy diagram where you have to know which is higher in energy and why, just like you did with the acyclic alkanes, is pretty important. Now, this chair has no ring strain. Right, my chair conformation has no ring strain. There's no angle strain, no ring strain. The angles are 109.5. There's no torsional strain. Everything is staggered. Every other possible conformation that was listed on that chart has got some amount of angle or torsional or ring strain. You need to be able to draw the chair. This takes practice because you have to be able to draw a nice chair that gives us some information when we are able to put substituents on it. This chart is from our book and gives us sort of a tutorial on how to draw the chair. I really don't use this. I just go sort of down, up, down, up, down, up, and I make my chair that way. Then I always go, when I draw bonds to the chair, up, down, up, down, up, down. Those would be what we're going to call axial because they're straight up and down. And then I have bonds that go off to the side. If my axial is up, my equatorial is down. If my axial is down, this bond is up. I have this axial up, so this is down. This one will be up. This one will be down. This one will be up. So you need to be able to draw a chair. You start with just drawing the cyclic part, and then you want to be able to add in bonds because those bonds are going to be really important. So if you draw things correctly, you're going to have 3 sets of parallel lines. And this takes some practice in order to do this. Every carbon has 2 substituents, right? There's 2 other bonds to it besides carbon. One is going to be axial, which is up and down, and one is equatorial, which is this sideways positioning. These axial and equatorial bonds are really important and you need to be able to draw them. That's really important. What you don't want to do is draw a fishtail. If I just do that, this is a fishtail and really doesn't show any direction to either of the bonds that are connected to this carbon. One has to be up and down. One has to be to the side. I have to be able to tell which one is up and which one is down. I have to be able to tell which is axial and which is equatorial on every single carbon. So this will not be acceptable for homework and tests and quizzes and whatnot. So to add the axial substituents, I start at the corners and I literally go up, down, up, down, up, down as I go around the ring. The equatorial groups are harder, but they run parallel to the lines in the chair. So this equatorial is going to go up. This equatorial is up. This equatorial is down. This equatorial is down. But do you see how they're running parallel to those parallel lines on the chair? As I go around the ring, if my axial goes up, my equatorial goes down. If my axial goes down, my equatorial goes up, and so on and so forth. Otherwise, I'm not going to be able to tell and differentiate between those different substituents. This is really important when I have substituents on the ring. If I have one substituent, which is a monosubstituted cyclohexane, I have two different chair conformations. When I do this ring flip, when I go through that series of changes that goes on that energy diagram from the one chair to the other chair, what happens when I have a substituent is that those substituents flip. The ring flips. Here I have my foot, here I have my head in my chair. Now my head is on the left side and my foot is on the right. If something is axial in one chair, it becomes equatorial in the other chair. So I'm going to go ahead and build a molecule that shows you this. And I am going to share the screen again. So I'm just going to randomly put a yellow ball here. So this is my chair that has a yellow ball. All right. So here's my foot and my chair, and here's my head. I'm looking at carbon 1 and carbon 4. As carbon 1 goes up, right, carbon 4 is going to come down. And notice what I just did. I just did a ring flip. This was equatorial, and now it's axial. This was the foot, and now it's the head. And I can go back by bringing this down. Notice this is equatorial or axial. If I go and do the flip, what I'm going to get is this is in the equatorial position again. So there's two chair conformations when I have a monosubstituted cyclohexane. One, they're the same compound. Again, no bonds are broken. I didn't do any chemistry. I'm just changing the bonds. I am literally flipping bonds around. I'm rotating bonds. But in the cyclic structure, they're not doing a rotation like we normally consider. They're just bending and moving, and I'm just flipping between those ring conformations. from one side to the other, and I'm going through all those other conformations when I go through and do that. So this was equatorial, and this one, this is my foot of my chair. And then when I go to the other ring flip, my yellow ball is now axial, and this is now the head of my chair. So I just did this ring flip by just moving the atoms and sort of using motion to go from one to the other. Oopsies. All right, so I showed you this ring flip. When I look at methylcyclohexane, now when I think about the two different chair conformations, I have this where the methyl is axial, or I have this where the methyl is equatorial. Larger groups in the equatorial positions are much better because they are more stable. There's less steric interactions that are destabilizing if my methyl group is in the equatorial position. So I can show you this by looking at the ring that we just had. So I'm going to add a methyl group in the place of my yellow substituent from last time. So here I have it. I have the methyl group, which is in the axial. Notice this is really crowded up here. I have 1, 3, this is on carbon 1, carbon 2, carbon 3, carbon 1, carbon 2, carbon 3. These are 1, 3 diaxial interactions where you can see that that methyl group is just sort of spinning around and creating problem and sort of knocking into that. When I do the chair flip, what I'm going to notice when this is an equatorial methyl, now I have all this space out here. That's why it's a lot more stable. I don't have those. The only thing that I have that is 1, 3 diaxial are going to be the hydrogens. Well, it's much better to have the hydrogens in those positions than this large methyl group. So if I have a large group, what I want to have is my larger group in an equatorial position. If my larger group is equatorial, that's going to be more stable. More than 95% of all of these molecules will be found in this conformation at room temperature. This has these hydrogens here, which really crowd that position. So the steric strain that results from a substituent being in the axial position is indicated here. When this is large, I have this strain in those, if I call this 1, 2, 3, and I call this 1, 2, 3, these are 1, 3, because the interaction is on 1 and a 3rd carbon to it, right? Those interactions are gauche interactions. They're not present if my methyl group is equatorial. So the rule is, if you want to project the more stable conformation of a cyclohexane that has a substituent, the larger group is going to go in an equatorial position. Larger groups cause more steric crowding. The larger the group, the worse it can get. So notice tert-butyl groups in those positions. I have basically 9,991 molecules to 1 because that tert butyl group has got 3 methyl groups on the carbon sticking up. Now talk about a 1,3 diaxial interaction. This is huge. This is isopropyl. This is that tert butyl. This is just an ethyl. But again, unless it's really small, I have a significant preponderance of the equatorial conformation being populated versus the axial. So this equatorial to axial ratio at equilibrium allows me to see which one is more stable and by how much it's stable, and I can measure these energy differences. Okay, that is going to be the end of this one, and then we're going to talk about what happens when I have more than one substituent in our next discussion. So I will see you in a little bit.